floor is yours, Sven.
Thank you very much for the introduction and for the invitation. It's my pleasure to be here, and I have made you a very new presentation about my view of ALD for catalysis, past, present, and future. And there will be even some new things coming from the past in this presentation. So I will talk. I decided that before I go to ALD for catalysis, I will introduce ALD in general, because thinking of this place, this is now a birthplace of a company that's important in particle ALD, and ALD for catalysis has been worked on here. But I do think that, like more in general, ALD is not so big in Delft. So I thought that because the particle ALD and the ALD for catalysis is actually a niche in ALD, I thought that it would make sense to introduce the big picture of ALD first. And then I'll move to ALD for catalysis, and I, here in this presentation, limit it to just the regular thermal catalysis. Because there's also, I think, new things to talk about there related to history and also what I've been working at Aalto University. And then, well, I promised to talk about the future, so then I have collected a little bit of visions for that, that also. And, well, probably depending on the day, the visions might be a little bit different, but there's something anyway. And by the way, I am trying to record this talk. I hope that's okay for everyone. I would like to share it with my colleagues and also some of the people who are not here today. Okay, first about ALD in general. What it is, where it came from, and where it's applied globally. And indeed, we've mentioned already Tuomo Suntola and the Millennium Technology Prize. That picture is from Tuomo at the event where he got the prize. So what is ALD? Well, it's a method to make materials, to grow materials. It's based on gas-solid reactions or adsorption, where the adsorption steps, they are saturating and irreversible. You start from some solid surface. It must have some reactive sites on it which can adsorb molecules. Otherwise, you will not have ALD happening. And then it uses typically at least two reactants. I call them here reactant A and reactant B. So you bring in the first reactant through gas phase to the surface. It reacts, and it reacts until saturation has taken place. So the full surface is covered with adsorbed species, and whatever excess you have there, that is removed either by purge or evacuation. So then after this first reaction is completed, then you have a well-defined surface. And if you look at the, here I have actually the process with time, so you just bring in the partial pressure of reactant A to the surface, and that's where adsorption happens. And so this would be the coverage, theta, coverage of chemical species. And if you would look at things as function of time, like mass change, it happens quickly in the beginning, and then when the reaction is completed, then nothing happens anymore. So this is not a continuous process, it's a transient process. Then you bring in the reactant B, and it reacts with the surface. Again, the extras are purged or evacuated. The partial pressure is there, the reactor brings the partial pressure there, and the coverage of the first species goes to 0 ideally, and the second species goes to 1, and again you are adding or sometimes removing mass from the surface, and you end up growing a little layer in this. And these cycles, then you repeat, they look exactly the same, except that there can be some surface effects, and the layer grows this way. And this process is exactly the same, whether you are talking about catalysts and particles or planar wafers. And yeah, sometimes you just do one cycle or a few cycles or thousands of cycles. It's the same thing. A few years ago, we published jointly with Ruth and Aris and first ever Kirk-Ottmer encyclopedia chapter on ALD. That's where this figure is from. You can also find it in Wikimedia Commons, where we separately published in advance all these figures with Creative Commons license so that everyone can reuse use them as you wish. Okay, where did ALD come from? Well, Suntola came up with the concept of ALD in Finland in 1974, 50 years ago. And his goal was to make thin film displays. So at that time, of course, there were no flat displays anywhere. He wanted to make them actually to be used in hospitals and so where you don't have much space for monitors. That was the original idea. And he wanted to make electroluminescent displays working on high voltage to create the light. And he started with zinc sulfide films. The first process was based on actually elements as reactants, just zinc and sulfur. And they were placed, he built a reactor where they were heated, zinc up to 360 degrees and sulfur to 100 degrees. And it was a rotary reactor where glass substrate was then rotated between these chambers. And he had calculated in advance that if you get one monolayer per cycle, like they thought you would, that you should get a purple reflection from the glass after a certain time, because it was 2 cycles per second that they did, and the first experiment was made, and well, they were expecting something and getting something else. So growth happened, the experiment was successful, but they didn't get as thick a film as they thought, but about 1/3 of it, and they were disappointed. Well, you could also be really happy if the first experiment is successful, but they repeated it, and the same thing happened. And after a lot of analysis and thinking, they understood that it's a surface reconstructions and so that are leading to this less than monolayer growth. Long story short, it took about 10 years before the product was ready. So the goal was to make these displays, and they were made. And they were sold for tens of years in Finland. The productions ended actually end of last year. This history has now finished. But anyway, here is a picture of the team, young Tuomo Suntola, and then here a little bit older Tuomo Suntola. So this is the beginning of ALD in Finland. Not yet semiconductor applications, but thin film applications, or applications on planar things. We also know of this other origin of ALD nowadays. So in Finland, Tuomo Suntola called it atomic layer epitaxy. In St. Petersburg, in the Soviet Union, the researchers have also come up basically with the same ideas, applying saturating irreversible reactions on totally different types of applications and substrates. So here is a picture of Valentin Aleskovsky, who in his thesis, I think this was the habilitation thesis in 1952, he proposed a framework hypothesis where you have like one big macromolecule, solid, like think of silicon dioxide, silica, and it with different functional groups, think of hydroxyl groups. You can easily imagine this representing silica, which they actually worked with. And he came up with the idea that you can work with these functional groups, react them further, convert them further, and that led to molecular layering, or molekyljarnaje naslaivanje, as they were calling it. And again, making a long story short, they were, for example, making a flow reactor. To my understanding, this is for molecular layering. I have, by the way, taken these pictures from the essay written by Maligin et al. You can access it here, and the previous one was from an essay. I'll go back this way. This is from also an essay, now on Tuomo Suntola's atomic layer epitaxy that I wrote. And so the Russians, Aleskovsky, Kautso and collaborators, it was academic work at the university. They were working with particles, porous materials, and you find in their early publications catalysts, sorbents, and rubber fillers as their goals or applications. And they indeed made those, so here is a scaled up reactor for making adsorbents. I think that was phosphorus and titanium based adsorber that they have then used in some equipment. So the Russian work never became very high, like large scale, but they anyway have ended up making these applications that others have used. And the chemical principles are identical. That has been confirmed. I've discussed with actually this person in the figure, Maligin. I've met him in St. Petersburg, and he has confirmed to me that he has met Suntola and he acknowledges it's the same technique. And Suntola also has told me that he has been in St. Petersburg visiting these people and recognizes that it's the same technique. There are no questions about that. How did then people learn about this history of the two separate inventions? Well, through conferences and through publications. And the Russians had learned about the Finnish works already in the 80s. They had read some publications. Most of the Finns learned about the Russian works first time in 1990, when there was the first ALE conference organized in Finland. This picture is from ALE 4 conference in Austria. So here is Viktor Drost, who I met in 2013. He came to pick me up from St. Petersburg railway station when I went to visit them. He did the same to Suntola 23 years earlier. So here they are in the same picture. Tuomo Suntola, Viktor Drost, Lauri Niinistö, who was the first Finnish professor to do academic research in the university where I come from, Matti Leskela, leader of Helsinki University for a long time, and here is also Stephen George from USA. So they have been in a conference and met each other. And here is a chapter from 2002 by Ritala and Leskela. I forgot now to write down, it's from a handbook of something. And here, table 1, alternative names to the ALD method. Here they are saying molecular layering dates back to old Russian literature. So it's there, but when I defended my thesis in 2002, that's pretty much what was said. And when I was a postdoc at IMEC, also Ruth mentioned this review article with a periodic table of ALD processes. That's when I was also trying to find out more about it. What did the Russians actually do? Was it older than the Finnish work, and is it really ALD? These were my questions, and I found the answers, yes and yes. And for that review, I made a table calling it Some Soviet-Russian ALD Investigations, and that word some is there because I noticed that when I was digging the literature, I found more, I found more, I found more, and it looked like that never stops. So I understood that there's a lot, and I made the point here that there's a lot, and I was hoping that others would pick it up and find more later, because it was too much work for one person. That was very clear. In 2013, jointly with international researchers, we started a virtual project on the history of ALD, finally to go through these works, to find out about them, and this is where Ruth has also been then of very, very valuable collaboration. And what we did, we tried to list all those early works and read them and, like, in our words, interpret what is actually there, because it had been difficult to find out about those works. For example, because not all of them had abstracts that you could find in Web of Science or so, and also the terminology might have been so different that even when you were using some search words, you wouldn't find them. But together with the St. Petersburg people also, we were able to compile this list. You can still find it in the internet. We gave posters and presentations, and then the main outcomes were these 4 papers. The 2 essays that I already mentioned, one about atomic layer epitaxy, another about molecular layering. Then there's a recommended reading list with 62 authors, is a co-author, for example, of early papers. And then I was coordinating this history project, so I have also written an ECS transactions paper about the learnings from this history project. Well, then the question is, how does this general view on the history get updated? Today, in 2024, I can say that it gets updated slowly. It gets updated incredibly slowly. So this is from, in 2002, there was already this mentioning that molecular layering dates back to old Russian literature. That's no secret. And I have had my table of these some Soviet-Russian investigations. Then a review paper was published. That's now the world's most cited ALD review. Mine is the second most cited. And well, it says that ALD dates back to the 1970s in Finland, period. Nothing about the Russians. Then there was a history review, AVS, American Vacuum Society journal, with 10 leading authors in the field. They had one paragraph about molecular layering, full with errors, and I have been discussing with many of the authors, and also in my learnings document I was pointing to some of those. And then 7 years later, an erratum was published, where first of all, the first paper didn't cite the review 2005, where I already pointed out these works. Now they added a citation to that review, but not to the one where I was discussing the errors. Anyway, this has now been corrected, that's good, and there's analysis of the erratum if someone wants in the history blog. But now it's 2024. We had last summer ALD conference in Finland with Ritala and Leskelä, the same guy from ALE4 conference, with Drost as chairman. And well, I would say the same old story here. This was celebrating 50 years of ALD, counting from 74, the Finnish invention. Suntola deserves all the credit. He was the first speaker, and that was really good. But the molecular layering was nowhere mentioned, just nowhere. And if you look at the atomic limits blog, that's nowadays attracting a lot of attention and sharing a lot of valuable information, they also posted a history update, and that starts from 1974. The molecular layering is nowhere to see. So when I went to St. Petersburg 2013 to start the history project, to start the collaborations, to meet the people, actually when I was giving a lecture a little bit like this at the Millennium University, there were about the same amount of people working with ALD present, listening to my talk. And the first question after my talk was, why haven't our works been cited? And that's a very valid question. And I think that question is still valid. And I'm willing to share these slides afterwards. So here I have at the bottom shared an example how you can actually credit one and not discredit the others. So when Tuomo Suntola got the Millennium Prize in Finland.fi, very official website, this prize was declared, and the Russians are nicely acknowledged there also. They didn't get the prize, but they still, their word is there. That's what is important for scientists, right? When you have done something, that you are not ignored, but your work is valued and cited. That's one of the very basic principles. All right, where is ALD applied globally? This is a collection from the Kirk Ottmer encyclopedia chapter in semiconductor industry, in the memory chips and in the logic chips. These are maybe a little bit older pictures of those. And the first, the electron display image, it was there for tens of years, but now it's no longer there. Then also in ride and read heads of hard disks and as protective coatings for silver objects and photovoltaics. These are applications that are big time used. And it appears that in this year also lithium-ion batteries have come to the commercial stage. Okay, now I used quite some time for that. Let's go to the ALD for catalysis. And I'm bringing another picture here. There's a lady appearing. So first, how ALD for catalysis started in Finland and in the world. Well, Microchemistry is a company that was founded by Tuomo Suntola in 1987. So he was leading that electroluminescent display development work, but when it started to become commercial, he stepped away from the leadership role there. And he founded a company where the purpose was to make photovoltaic panels, and catalysts was also one of the original aimed applications. And actually the history of ALD for catalysis started with a phone call. So Outi Krause, who was the lady in the picture, who was leading the catalysis team at Neste company, he got a call from the top of the Neste company telling her to call Suntola to talk about starting this research, and she did. And they had meetings in 1988 deciding to go for a test. And they had at that time activities using zinc on ZSM5 zeolite catalysts for converting butane to aromatics. They had this ongoing activity, and zinc had been used in the electroluminescent displays. It was also something that could be easily tried for catalysts, and that's what was done. Catalyst testing was done at Neste Puurunen facilities, and promising activity was seen. And that then led to a continuation to a study, and Kahlo Somorchai, somebody might know the name, was also involved. He was in the advisory board of Neste at that time. And this continuation, it led to more promising results and a patent application. And this was filed early 1990. It has zinc ZSM5 catalysts, rhenium on alumina catalyst, and chromium on silica catalyst for polymerization. And this history is not really easily findable. I have been discussing with Outi Krause, who is our professor emerita, and also looking at a book chapter by Lakuma et al. And the Suntola essay. So collecting these things together. Sorry. And the follow-up patent was filed quite soon. And what's interesting is that in this next patent, Kaltsov is already cited. So the Russian molecular layering works were cited. I am kind of a product of this research line. I made to do my doctoral thesis for ALD on catalysis, and for me, the Russians were just a normal part of scientific history, nothing hidden or so. And the first papers appeared in 1990s. I have here some mention, and I think that this one in the middle should be perhaps emphasized more than it nowadays is. So it's by Evelyn Lakuma, atomic layer epitaxy on porous substrates, showing 5 ways how the growth per cycle, or the surface density, how many metal atoms you can get in a reaction, how you can control it by heat treatment of the support, controlling the number of reactive sites, or blocking bonding sites if you want to lower the amount, if you get too much in a cycle, or to some extent the reaction temperature, or the size of the molecule, or the chemical reactivity, and growth of compound layers, meaning cycles. It's all there already. There were several doctoral theses made. I am there, the second one in this slide. I apologize for lots of text here. I have made these slides also to share afterwards. So the reactions that were studied at Aalto or Helsinki University of Technology. After Professor Krause became professor in 1993, she moved from Neste to the university. For example, chromium catalysts for dehydrogenation and some cobalt catalysts for hydroformylation and also hydrogenation catalysts. And in 2005, Outi gave an invited talk at the Pro2Tech about ALD for catalyst preparation. Well, that was Finland. I'm talking from the Aalto perspective, so I could start with that. What about the world? Molecular layering. They started with catalysis in mind. And the first paper I could find is from 1970. In this paper, called Smirnov, Aleskovsky, Smirnov is probably still alive, studied the decomposition of carbon tetrachloride with silica that had been modified with phosphorus and titanium. And look at this, it's from 1970 and it's in English. If someone has told you that these were not cited because they were all in Russian, this is from 1970 and it is in English. So that's not only Russian. There are follow-up papers for this, and I have been actually looking at our ALD history evolving file to find these because you don't find them cited in reviews. And I found 15 publications. So in addition to carbon tetrachloride hydrolysis, there was oxidation of benzene and something else to maleic anhydride. There is polymerization catalysts, also chromium on silica, and catalytic cracking. So quite a lot. And then also fluidized bed modeling, maybe the first significant modeling paper on ALD. That was USSR. Then there's also Japan. 1988, there is a paper from Asakura et al. Where zirconium oxide has been added on ZSM5 to convert methanol to isobentane. So yet another branch, so to say, and also follow-up studies for that. I will not go into the details, but just mentioning that there are different routes here. So Finland was not the first. It was, if you look at countries, it was not even the third because there was actually a Bulgarian thesis, habilitation thesis made, and also in Germany some works before. And now I'm here also during these days discussing of our next collaborative paper, which will be a review article where researchers from Roots Group have been digging into the literature, and here is the number of publications on catalysis, thermal catalysis ALD versus year of publication, and you see that from 2010 on, it's no more these sporadic papers, with Finland mostly as the origin, but USA has come strongly, China has come strongly to this field. And maybe there's a decline in the end that I realized yesterday. Okay, finally, let's talk about present. Some research examples from Aalto University, from my research. So, there has been a generation change of professors at Aalto University. Outi Krause, who has been one of those ladies who is breaking the glass ceilings, so to say, she became the vice president of Helsinki University of Technology, first and only female ever, and she was the first dean of our school when Aalto University was founded as a merger of 3 universities. And of course, when you become that kind of a leader, it means that the research is no more happening, really. And I came to Aalto University in 2017 to work with ALD and catalysis, and what we are using as tool is one F120 reactor designed by Suntola. in the 80s. That has been the tool, a fixed bed reactor. And even shared with another professor. So I've been there 7 years and we have some progress to report, but not so very much. But we have had one project where carbon dioxide is hydrogenated to methanol, where we have made catalysts by ALD. We started with zirconia. Why zirconia? Well, in this reaction, you are making per one molecule of methanol, you are making 1 molecule of water. And you could imagine that that water is problematic to the catalyst in the longer term. And zirconia should be able to handle water better than, for example, alumina that's in the traditional commercial catalyst. We have impregnated copper. We started with zinc, adding zinc by ALD. And something that you don't often see in catalysis papers is people think that because it's ALD and it's because these saturating reactions that you automatically get uniform coatings. I would not assume that. Actually, I have wanted to show that before we go to do more complex things, I want to show that we have good materials. So we have been freezing our ALD treated zirconia particles in a resin, cutting them and taking a cross section. And this is how our zinc content looks like. So we have zinc. Actually, it looks like it makes a little dip in the center. Anyway, we have zinc everywhere and we have gone to testing with these. We have tried this new zinc reactant or precursor, acetyl acetonate, because we were not able to use the pyrofluoric diethyl zinc that everyone else uses. And we have shown that you can also add zinc from this reactant, and it's not very temperature sensitive. Once you are below 200, you get about the same zinc amount irrespective of temperature, but if you go higher, then you start probably decomposing. And what is typical for ALD is that once you are pairing the surface area, we have been calcining our zirconia at different temperatures. Here the green spots show you the surface area, specific surface area. It's coming down strongly. Well, so is coming down the zinc content. But if you then calculate how many zinc atoms you have per square nanometer, that's always about 2 per square nanometer after one reaction. That's irrespective of the specific surface area or the calcination temperature of the support. If you then want to make cycles, increase the zinc loading, then you need to remove those acetyl acetonate ligands that are remaining on the surface. Typically, this is done with a heat treatment, and we have made actually an infrared study also, but this is with a mass spec looked at how CO2 is coming at different temperatures, and when we are above about 400 degrees centigrade, then we have removed those, we have burned them away. And we have made cycles, and the conclusion has been that we add about 2 per square nanometer in a cycle. And we also made low energy ion scattering analysis. Today I was recommending it to some of Ruth's students. So that beautifully shows that we start with this zirconia surface. It shows zirconium and oxygen, and when we add zinc, you directly see it, and the zinc signal goes down. But what this revealed to us was that we don't have that 2-dimensional growth mode. When we carry out 3 cycles, we don't cover as much of the surface in each cycle. We cover a lot in the first cycle and not much in the other cycles. We are adding zinc, but it's not covering our surface. So from that, we thought that what we are making is these types of clusters, that the zinc that's added likes to have zinc as neighbors, and maybe it's even going on top. I don't know. So kind of can you call it island growth? Perhaps you can. Then these were tested for activity, And what we did was we made a series of catalysts where, as said, copper was impregnated. We had either just copper on zirconia or just zinc on zirconia, or first zinc and then copper, or the other way around, first copper and then zinc, and we made also one where we have zinc, copper, zinc. And these were tested for activity, and we found that those catalysts where we had both copper and zinc present, and zinc on top, they were most active. So here you have the space-time yield of methanol at maybe, well, 500 kelvins has been our reference temperature. We investigated 3 temperatures. Yeah, the blue ones are always the best here, and the blue ones have zinc on top. Also, we had the least methane selectivity. So you would want to selectively make methanol, but you can also make CO and methane. And those had also the best selectivity. So of this tested series, we concluded that the so-called inverse catalysts, where you first had the copper and then zinc on top, they were the most active and selective. We have continued this series, but we have no publications of it yet, but trying also different supports, but we have actually not been able to find a better one than this zirconia. Then stepping or continuing from this, is the distribution uniform? Is the coating the same everywhere? So here we observe that little dip. We have made then experiments on totally other particles, spherical alumina, and we have varied the amount, the dose that we deliver in the fixed bed. And here you can see that, first of all, no, it's not always uniform, not at all. These had 1 millimeter as their size, so they are pretty big, and they are spherical, and clearly the higher dose we deliver, the deeper the film is growing, and it's easy to image this actually. So in addition to the targeted uniform distribution, it's very clear that we can also make eggshell catalysts this way. Whether it's useful, I don't know, but that's how ALD progresses. These have not been published elsewhere yet, and in Ji-Hong-Yim's doctoral thesis. Also about the research being done. So I'm kind of between the semiconductor world and the catalysis world, and conformality, or this how the film grows into 3D structures, it's actually interesting to both. So when working with those memory chips, for example, that are nowadays in the computers, the structures can be very demanding in 3D, and people need to develop processes that are able to penetrate there in a uniform way. So I have at VTT developed test chips for testing this, and we have been doing diffusion reaction modeling to analyze how ideally the film grows, and very recently this modeling was also extended to spheres, which is relevant to our current applications. So there's a paper in physical chemistry, chemical physics, where in addition to the slab modeling, which corresponds to the LHAR, that means lateral high aspect ratio test structure, they are basically the same, and how the coating penetrates as a square root function of exposure time, that's known, but then this sphere and cylinder modeling, that's more new. Not maybe surprising how it came up, but now those equations are out. And we have also been then, because it's actually quite complex, at least to me and my students, to think how changing these parameters will affect the penetration depth. We have a pure simulation paper out where you can much more easily vary these parameters than experimentally, and another one has just been accepted. I know it from yesterday in the same journal, and also then similar things for those spheres, and well, I could summarize it here that the coating goes, the deeper, the higher our channel height is when we are in Knudsen diffusion regime, and the higher the partial pressure. These are very logical. The higher the exposure time, the more lighter the reactant is. These are very logical. And then when we are varying the growth per cycle, this is something that has not been so logical. Generally, people think that the higher the growth per cycle, the better, but actually we see here the opposite effect, that the higher the growth per cycle, the less the film penetrates. So, because you could imagine that the surface is like a sticky mat, and it has a different density of sites that are bonding our metals. And if it's a high growth per cycle, then that sticky mat has very dense sites. And if it's a smaller growth per cycle, then the sites are bigger and there are less of them. So when you throw balls on that, they will go deeper and the growth per cycle is smaller. This is something that I don't know if I can explain it well yet, but we observe it in simulations. And to me it's now logical, but I've heard people telling otherwise as well. And what has also come out in these simulations is when we think how the partial pressure is changing inside. So when we have the slab model, it's just going linearly down. So it's something outside the structure, and then it starts going down linearly. But when we have those spheres, then it's this 3D shape of them that makes it follow a different like a curvature. And well, a model should be compared with experimental data, right? To show if or to check whether it has any sense. So when we have worked with these semiconductor type or maybe test structures that are also relevant to electrocatalysis, like you are working here with micron size features roughly. If you investigate how the actual experimental results compare with our predictions, they look pretty much the same. I'm not going to details because I think there's no time. And here is the first comparison of the sphere model with data. Also, it's from Jihong Yim's thesis. The orange one is the simulations, and the blue dots are experimental data. So it seems like that makes probably sense as well. But I think that it's now time to go to the future things. Oh yeah, I'm just gonna show, we have a new self-built ALD reactor. We have the first results that were shown this summer, and I promised to someone to show some temperature spikes here. So I'll just jump to that. We have been flowing zinc acetyl acetonate, first heat treating, then coming down to about 200 degrees centigrade. And we are able to measure the exothermic reactions when we start feeding. We have a temperature probe in the bed, and the bottom heats the most. That's just a very quick note. These types of results are not yet there in the literature, but it has been reported by some others also that these temperature rises are expected. Okay, visions and needs, I'm going to go through very quickly. I think that we should know about the history and we should acknowledge it, and the history of ALD has not been treated well in the literature. We should do much better job. So there are lots of misstatements around there. So when you write your papers, I recommend to check the original sources. I'm just going to skip this, go through that so quickly. So my visions, I think that first of all, semiconductor industry is very big. It's $1 billion industry for ALD. That helps also other applications such as catalysis, electrocatalysis, and so on. They are developing new reactants and we can make use of that. That's going to continue. I think that these ALD-made model catalysts will help fundamental science to progress. By ALD you can make things in a controlled way, in a reproducible way. Then there are lots of papers on single atoms, on coatings to slow down the activation, and mixed metals being made by ALD, zeolites and MOFs. I think that this interest will continue. Environmental analysis of ALD processes, this seems to be starting, and I also think that there will be still more intimate collaboration between experimentalists and theoreticians. I do hope that people will study the conformality and the distribution. So there are examples where you get exactly the same intensity of metal throughout. Here I have some examples. One from Delft showing that in the middle titanium throughout the particle, but some concentrations on the outside. And then there's on the right you have a case where our colleagues observed TMA water coating titanium particles only on the outside. I think that there was a surprise of how little the coating had penetrated. So if you assume it's a uniform coating, you might go very wrong. And I think that there's probably literature around where this assumption has been made. And I'm very much a friend of open science, but I'll go through this quickly because time is flying. The virtual project on history of ALD, that was a true open science project. We could realize things there that no one could have done alone. And I am in much favor of sharing data. I don't know how you are doing it nowadays here. I'll be happy to discuss afterwards. From my group, we have shared a few data sets in Zenodo. It's quite some effort, but I think it's worth doing it. So sharing data, sharing software. I'm in favor of that, but it should be done, so to say, sustainably. So we need to think also of our workload. We cannot share everything. We need to choose what we share. It's impossible to share everything. So this is my final slide. Maybe I just let you read it, and then I have added a third person there because I was happy to be participating in this Millennium Prize ceremony, and that's why I have had to skip being part of a doctoral defense here. Surprise to Ruth then. So, thanks for listening.
Thank you very much, for a great talk.